morning everyone. So, the last class we talked about large confidence intervals for large population and small population. So, large population, when we give confidence intervals for x bar, it is typically from normal distribution due to central limit theorem, right, and the central limit theorem applies because you assume that the sample size is large enough and sample the population, underlying population is independent, okay, those are the assumptions. And now, so keep in mind the sample is underlying population is independent is one assumption we make, important. And when it comes to small sample, that is less than 30, that is where the issue is. You many times will have less than 30 samples as well. If you want to do some kind of statistical analysis, then you actually need to make an assumption that the underlying distribution is, population distribution is normal, which is actually restrictive. So, you have to make the underlying distribution to be normal, assume it to be normal. Once it is assumed normal, then you can do what is called as a t distribution, because your confidence interval comes from t distribution, because your x bar is distributed using is t distributed, okay, and you can see t and normal merges after sample size of greater than 30, and that is the reason why I kept saying 30, okay, clear. So, that was the last class, and then we actually started looking at what is known as sampling distribution of p hat. So, when you talk about proportions, for proportions as well you could give sampling intervals, right. So, you are talking about sampling distribution of p hat, which is we know what is p hat, and then we know the variance of p hat, which is variance of x bar is sigma by root n, sigma squared by n. So, standard deviation is sigma over root n. Similarly, sigma p hat is pq square root of pq by n, okay. This is the what I call the distribution of, the variance of standard deviation of p hat, and it all comes from pq. npq is what is your standard deviation is, right, npq is your standard deviation. So, you replace q with 1 minus p and then do it, so you will be able to get this sigma p hat, variance of p hat, okay. And for large samples, the sampling distribution of p hat is approximately normal. So, p hat distribution is also normal, you do not have any underlying assumption, this is again from central limit theorem, okay. So, for large samples you do not have an assumption on the underlying distribution except for what is assumed in central limit theorem, okay. The large here means not the samples, but large means the p hat plus or minus 3 sigma hat should be between 0 to 1, okay. P hat is always between 0 to 1, all I am saying it p hat plus or minus plus 3 plus or minus 3 sigma p hat should be less than 1, right. For large samples, if this is obeyed, then it is still fine, okay, that is what it means by large. So, we have the sampling distribution, again p plus z alpha by 2 into sigma p hat, p minus z alpha by 2 into sigma p hat. So, for proportions also your underlying distribution is normal, p hat distribution is normal, and therefore you can give the confidence intervals just like what you did for x bar. So, I have solved a problem here, so you can go look at it, okay. And then you have this what is known as a determining the sample size. Suppose I am interested in a certain error, how do I calculate the sample size required, right. So, I want to assert my statement, I have to be 95% confident, okay, about something, about let us say x bar, about mu, the range, okay, I have to be 95% confident about the range of mu. Let us ask this question, about the range of mu I have to be 95% confident, okay. What should be my n value? That is the question you are asking, right. So, if you want to be 95% sure about the range, then what do? You start finding out the appropriate mu lies between what, x bar plus or minus z alpha by 2 into sigma over root n. So, what is the error we are talking about between mu and x bar, what is the error? This is what we are talking about, right. Of course, Z alpha by 2 is fixed, right. So, this is what we are talking about, the standard error is Z alpha by 2 into sigma over root n. Now, Z alpha by 2 is known to you. If you want a 95% confidence, you know what is Z alpha by 2, it is 1.96, right, and if you want 98, 99%, you know it is 2 point something, right. So, using this you can figure out the value of n, using this you can figure out the value of n, right. So, n is Z alpha by 2 squared sigma squared by SC squared. So, now what are you fixing? You are fixing Z alpha by 2, that is I want to be 95% confident that mu lies within this range. What is the statement I want to make? I want to make a statement, I am 95% confident that mu lies within this range. If I want to make this statement, how many samples should I collect? That is the question we are answering here, okay, clear. So, what are we trying to answer? We are trying to answer, I want to be 95% or 99% sure that my mu lies within this range, and it is not a possibility, you can keep on increasing 99.9 etc. I want to be that much percentage sure that mu lies within this bounds, okay. So, that bounds is nothing but your standard error, okay. Confidence comes in Z alpha by 2, both these numbers are fixed, and of course you do not know sigma squared, so you replace with, what do you replace with? Of course you do not have any clue, so you have to replace with S squared, okay. So, now you will get the value of n. When will n increase? If you want the bound to be, variance is the last thing, right. If you want the bound to be very small, then n will increase, because standard error is in the denominator, right. So, if your error is less than 0.1, let us say, then your denominator becomes 0.01, 0.1 square, 0.01, right, then n will actually double, right. So, n will increase if you want a tighter bound, which is what makes sense, and n will increase when you want to be highly sure. Your confidence level, if it increases, n has to increase. Suppose I want to be 99% sure, then Z alpha by 2 will be higher, and therefore Z alpha by 2 the whole square will also be higher, contributing to more n, larger n requirement. So, that is what. So, when you want to make a claim which is very sure, you should be very highly sure, but at the same time bound is very small, then n will blow up, and of course n depends on sigma squared. So, if the underlying population is widely distributed, which you know in biomedical engineering is the case, the value of n requirement will be really large. So, that is why data is the fuel in biomedical engineering, because your underlying distribution itself will have a larger variance, okay. So, that will command for more n, and if you want to be very sure, Z alpha by 2 will go up, n will go up, and if you want the bound to be tighter, standard error has to decrease, which will also lead to increase in n. So, that is the relationship between n, standard error, confidence, and your variance of the underlying population, okay. So, that summarizes it all. This one equation or one relation summarizes everything, okay. How to choose n, what are you trading off, okay, clear. Any questions? So, if you go down in n, you are compromising on all three. So, what do you want to fix? Whether you want to fix standard error, whether you want to fix percentage of accuracy, I mean confidence, or you do not have a say about the underlying population distribution, right. So, if it is small, then it is nice, but not sure whether it will be small in biomedical, it will most likely be larger, clear. So, we always take S from a instead of a what I call sigma squared, okay. I have given an example, I will leave it to you guys, okay, because these are simple examples, I expect you to do the same. The same holds good for your proportions as well, right. Your proportions also, standard error is nothing but z alpha by 2 into square root of pq by n, because that is what mu plus or minus mu equals to x bar plus or minus z alpha by 2 into standard deviation. Standard deviation of proportion is nothing but square root of pq by n. So that is my standard error. So you plug in this, you have the standard formula.